Now I'll show you the EAF process calculation by using the package step by step. So this was slide I showed you before about the EAF calculation. So we want to set up all the ore and the flux and then carbon as the input and with the initial condition. So let's look at this one. So I already set up actually those calculation here. So here, the very first thing you always have to do is you have to go to the database selection and you have to select the proper database. So in this case, as I show you, we need packed PS database, FT oxide database, and FS steel database. So these three is the key database. And say OK. And then you have to now go to your unit section. So it's a temperature and etc. So if you don't like this one, you move your mouse here on top of this unit and do the mouse left click. Then you can see the small actually the menu to change your unit. So I prefer actually the Celsius. So I'm using Celsius, ATM, and then energy in joule, and then quantity in gram. So if you don't like, for example, energy in joule, if you want kilowatt per hour, you can change it in this way too. Okay, say okay. And then you have to enter your mineral name. So the formula for the mineral. So MnO2. So this kind of formula is very important, especially when you use your initial condition, because depending on your name and the phase here, depending on this phase and the temperature, your energy is automatically calculated as a starting point. Okay. So I add 450 MnO2 and then 350 Mn2O3, 70 gram of the Fe2O3, and etc. And then I'm adding A amount of carbon. As you know, in the FACSA, the variable, in order to actually change the amount as a variable, we have to use the A. Okay, so open bracket A and then close bracket. And of course, you can change this A in the many different forms. So for example, you can say 100A or 100 minus 5A, whatever you like. Okay, and whatever you like to change it as equation, each kind of linear equation, you have to enter inside of this the bracket. Okay, and then if you don't click actually this initial condition, it looks like this. There's no phase information. So without initial condition, the fact says only taking the mass as input and no energy actually they consider in the initial condition. But if you click the initial condition, the fact says consider both mass balance and then also energy balance, considering that starting phase as starting actually the species of your calculation. So if you click this one, you can see many different phase actually showing up. So theoretically, it's better to take FT oxide as if it is available, FT oxide would be more accurate. So FT oxide is better. So for example, this one too, if you like, you can take FT oxide. Okay, and so this one also from the FT oxide. But most of this actually is similar, so it doesn't matter. But if you like, you can change one by one in this way. Okay. And then you have to set your initial temperature of your component you want to enter into your furnace here. And so I say 25 degrees Celsius, but sometimes you might have the different temperature depending on the different mineral. So if you have the one bucket and the other bucket with a different kinds of the minerals, and you can have different temperature as an incoming material too. So in that case, you can change also initial temperature differently. So for example, in this case, if I say I want to enter Mn2O3 from the 500 degrees Celsius, you can set 500 degree. But if you do that, all of them is changing simultaneously because all this one is the same under the same stream number. So typically in the fact stage, if you are in the same stream number, we consider that all this one is coming from the same temperature and same pressure. So in order to change it actually different temperature, different input actually the initial temperature and pressure, you have to change the name of the stream number here. So for example, if I say this is the stream number 2, then I can freely change this one now, 25 degrees Celsius. And it doesn't change the other one. Okay? Or if you want to 1, then it's going back. Yeah. So in this case, I'll set everything as 25 degrees. Okay, so this is the one thing you can also remember in the energy balance calculation. And then you go to the next, and then you have to select all the phases. For example, if you start from the beginning, you will be like this. So there's no phase selection, of course. And so you can select one by one, or in this case, you can go select button here, and then select all solutions, because we believe that all this data is good enough in this calculation. So you can select all of them if you like. And then you can also go to the pure solid in this actually the empty button here. And if you do the mouse left click, it will select all the possible solid phase. And typically when you have this kind of star, it means you have some custom selection, because for example, if you do the mouse right click on top of the pure solid, you can see that what kind of solid phase is selected. And then there's the, for example, duplicate and select it. So it means when you look at this kind of carbon in the PACT-PS database, and this is also available in some other database. So for example, FS Steel database containing the carbon. And then we actually set this kind of selection criteria. So instead of taking the carbon from the two different databases simultaneously, we are taking the carbon from the more reliable database. In this case, we put all the metallic element is can be first taken from the FS Steel database, because we believe that FS Steel database is more accurate than the PACT-PS database. And also all the possible oxide can be taken from the FT oxide database, because FT oxide database is more well evaluated oxide database than the PACT-PS database. And then if nothing is available, then we are taking from the PACT-PS database. That's typical actual priority we set up in the database selection. So it's a kind of pre-selection criteria. And so that's all done automatically. So in this way, we can remove the duplicate kind of phase selection. And then you do the same thing for the gas phase. And of course, in the gas phase, in the selection of gas phase, we prefer to select the PACT-PS database as a priority database. Okay, and the pure liquid, you don't need it, because the liquid iron or liquid manganese and the pure liquid is part of the liquid solution of the alloys. And also pure MnO, pure CaO, this kind of the liquid phase is also part of the slag phase. So you don't need pure liquid in the most of the time. And if you select the pure liquid, typically you see that there's some kind of the warning message and say that you don't, we recommend that don't use the pure liquid phase. Okay, that's good. And then you can select your final temperature, final pressure, and then you can change the amount of the A, which we set as carbon here. So A, we are changing from 0 space 300 space 300 space 10. It means initial condition, final condition, the step of the calculation. So I want to do the calculation of the carbon from 0 to 300 with every 10 increasement. That's what it actually meant in this actually the setting. Okay, and then you can do normal or normal transition if you want to see even where's exactly the transition happening. Then it will even calculate what's the exact A value, where's the transition happening. But I don't want to bother it too much. So in this case, I'm simply using normal calculation and then go click. Okay, then in a few seconds, you can see the result like this. So here we have A equal to 0. So initial condition without any addition of the carbon. So all this phase which I enter is heated up to the 1500 degrees Celsius. That's what it is. And while it is heating up, you can have some amount of the gas phase is forming, and then some amount of slag is forming. And then if you go down, all the other one is 0, 0, 0, 0. And if you scroll it down further, and even the stoichiometric phase is all 0. So it means there's only this kind of gas phase and this kind of slag phase is forming. And the purpose of this EAF actually the process is to reduce the manganese oxide to the manganese metal So we have to reduce this actually the oxide slag to the manganese metal. So if you click one by one, you can see how that evolve. And then if you go, for example, 230, as I show you in the presentation, you can see that this is the initial condition, and now A equal to 230. Under that condition, you have 17 moles of the gas phase, and in gram, 485. And this is CO and the manganese, actually the composition inside of gas. And then this is the amount of the liquid phase total in the metallic liquid phase. And then this is the component inside of the liquid metal. So as I mentioned before, instead of using this one, it's better to use this one as a overall composition of the liquid phase. So if you do the, for example, ICP analysis for your liquid phase, and you have to compare that with this result here, okay? So carbon is about 5.2% and iron is about 9.5%, as you can see. And there's also a certain amount of silicon. I think this is silicon is actually reduced and then enter into the liquid metal, okay, 0.26%. And then there's certain amount of slag. So 220 grams of slag is forming, and then this is composition of the slag, okay? And then all the other one is all 0. And then if you go down all this calculation, the one thing you have to look at is, if you go down further and further and further, you can see that there's the delta H and H. This is very important, actually, the information you have to look at it. So H means you are kind of the absolute enthalpy value in the your last stage. So it means at the 51 degrees final stage, at this A condition, what would be your enthalpy of the system? That's what it's showing, okay? But if you want to see the difference between your initial condition and this final, actually the chemical reaction condition, you have to look at delta H. So this is actually related to your energy balance, okay, from the initial to the final. So 4.6, so 4.6 gigajoule of the energy you need, okay. Okay, so this show you all the data, all the thing we actually mentioned before. And now if you want to plot the result, I think you can go output simply, and then go plot, and then plot result. And then you can set up your axis, x-axis and y-axis, for example. Axis, and then you say that y variable, okay, you can say in gram, and so gram of the old phase, that's what I want to do. And the x-axis as alpha, because alpha is the main variable we are changing here. And then refresh and say okay. And then when you say gram, you have to select what kind of the gram you want to select, okay? So you have to go select, and then you can select one by one here by looking at the number here, but it's very confusing. And you can go simply select all stable phases. Then you can say that there's 11 species is selected, and then say okay, and then plot. Then you can see the result like this. So you can see that in the y-axis is gram, and the x-axis is the amount of the alpha you buried. And if you click one by one, you can see this is slag, and this is MEO, as you see it here too, and this is gas amount, and this is liquid metallic amount, okay, pairing with the amount of the A. As I actually explained in the presentation file, about 225, I think as you see here, there's only liquid slag and liquid metal and gas phases forming, okay? So the editing of the figure, I think you can find it in some other slide to learn, okay? Then let's close this one. And then we can plot also something else. The most important one is this delta H, as I show you here. So this is showing you the energy balance between the initial condition and your final condition. And then refresh and say okay. And then for the energy balance, delta H, you don't have to select the species, because delta H is the system kind of the property. So it's not specified by some species or some solution you actually produce. So it's a delta H. You don't need a selection of the phase. And then just simply plot. Then you can see this kind of the variable with alpha. As we say that about 225 here, the energy balance is about 45 gigajoule in this case. Okay, and then let's close it. And then also the other selection I show you was the weight percent of the species. So here you have to be a little bit careful. Gram and the weight percent. Gram show you what's the absolute amount of each solution phase or each component in the solution phase, depending on how you're selecting it. And if you select the weight percent of solution species, it means within the solution phase, for example, slag, what's the weight percent of CaO or Ca, or within the liquid phase, liquid metallic phase, what's the weight percent of the iron, carbon, silicon, manganese, and etc. So if you want to see the actual composition of the each phase, you have to select this one. Okay, and then refresh, say okay, and then now you have to go and select it. So if you go, there's 11 species previously selected in the previous plot, so you have to clear them again, and then you have to now go down and select. So I mean the phase selection is a little bit tricky sometimes, so let's look at this way. So this one show you, okay, the amount of the each species, okay, and this is actually so mole, and then this is the mole fraction and activity and etc. So I mean you don't see it in the weight percent, but you see that there's something change in mole, so it means there's some species like this existing in the liquid phase, okay. And but when you look at this one, this is carbon and silicon, and there's the CaO species, and this is based on the your modeling species. And so this is similar to the what I show you before as this species, CaO. Can you see this one? Okay. And but we want to plot this mass fraction or weight percent of all mass fraction, okay, as element. Then what you have to do is you have to go down in the end of this actually the phase selection. So in the end of this phase selection, you can see that there's the total amount of the solution. And then when you go further down, there's elemental distribution of the each species, elemental distribution of the each element inside of the each solution phase. So here you see liquid phase. So this is the liquid, actually the component as element. Okay, and then you say okay, and then plot. Then you can see the elemental distribution of the species inside of your liquid method. Okay. Okay, so just be careful about weight percent, and then also even when you select the weight percent, and you have to know exactly what kind of species you have to take it, and do you want to take it as a modeling species, or do you want to take it as elemental species? In this case, we want to plot it as element in the solution, so we have to take it from the proper place. Okay. Now, let's go back here. So so once you finish the EAF process, we have to think about, okay, the oxygen converting process. So in the example I show you, we make a stream, actually the solution, stream of the liquid iron or liquid ferromanganese from the fresh element we enter from actually the tap here. So for example, we make actually stream by entering each of these elements from the beginning again. So this is the one of the way. And the other way we can do it is, we can do it here. So for example, let's assume that the A at 230, and this liquid phase is the good liquid phase. We want to take it for the converting process. Then we can take this one as a stream file too. So for example, let's try that. So output, and then go stream file, and then save stream file, and then which stream file? Here, liquid. Okay, so if you click this one, then you're going to ask, okay, what kind of name you want to use? So FEAL, and I make this one A equal to 230, for example, at 1500 degrees Celsius. So I want to use this one as a name. And then if you save it, it will save this one as a mixture. And then you can say that, okay, this is by default this name, but if you don't like it, you can change it too. And in this way, I'm saving this amount and then this chemistry and then the energy involved in this actual liquid phase. Okay, so the enthalpy and Gibbs energy of the decomposition of the liquid phase at the 1500 degrees Celsius will be saved in this way. Save, say okay. So now it's ready. I can use ready to use this actually the output as input for the next calculation. So now let's start the oxygen converting process by using the ferromanganese alloys I just saved from the EAF process. So in the EAF process, I saved this stream file here, and I want to enter the oxygen and some flux like this, and then start doing the adiabatic calculation with changing of the oxygen amount, and to see how we can remove the carbon in the oxygen converting process. So for that, let's start to enter the species like this here. So I'm just keeping the same database selection as before, sorry, and then same unit as before, and I'm just simply entering species here. So first one was the oxygen and CaO and the MgO, and the oxygen I'm using a variable, okay, and then CaO I'm using another variable or constant where we can set in the factory 0.8 B and then 0.2 B. So B in the fact stage we call it as beta, and beta is the constant value we can set in the each calculation, and A is the alpha which can be varied during the calculation. Okay. So by setting this way, for example, if you are setting B as 1, it means 0.8 gram of CaO, 0.2 gram of MgO is entered in the calculation. Okay. The last one is now the ferromanganese, the stream file we saved it before. And in order to actually in order to enter the stream file as input here, you cannot use actually the species name directly. The only way is you prepare the column like this, and then on the species name, you have to go to the edit, and then mixture and stream, and then import stream you saved before. So the stream we saved before was the FEMN at the A260, this one, 230, sorry, this one, save it. And then you can see that what's the amount. As you can see, the amount is 511 gram, and then the composition is iron, manganese, calcium, silicon, oxygen, and carbon. You can see it, and the temperature is 1500 degrees Celsius. Because and then it's also saying it is stream. Unfortunately, even you want to change it, it doesn't change the temperature because stream is the saved at the certain temperature with all the enthalpy, all the Gibbs energy, and etc., as well as all the amount. So if you take 100%, you'll take entire amount as in the calculation. You can actually make it 1000% if you like make it at 10 times more, or you can take part of that by taking, for example, 50%. You can take part of the previous actually the stream in this calculation too. Okay, and so if you look at stream number 1 and 2, and so I don't like this temperature, I want to change it to 25 degrees Celsius as input for this one. So that's all set. Okay, and then let's click next, and then I'm selecting all the solution, all the solid, all the gas phase as before, and instead of the taking the final temperature as input, I'm going to enter delta H equal to 0. It means adiabatic calculation. Okay, and then B I want to set 0.3, and then A here from 0 to 10 every 1, as I show you just before in this actually simulation. Okay, so we may expect a little bit different result because the input of the ferromanganese here is different from the input I used in this PowerPoint actually the presentation. Okay, so let's see how big difference we can get. Okay, so and then you can say calculate. Before I just do the calculate, I'll show you there's the normal and open actually the option. So normal option is just as it is, just doing 10 calculation. And then open option here is activate when you use the variable for the gas species, A variable in the gas species, then open calculation can be activated. And the open calculation means you are injecting certain amount of the A value in the calculation, and then if there's solid liquid gas is forming, then they are taking gas out and then keep the only solid and the liquid phase in the next calculation, and then add additional amount of A until the step you want to actually calculate. Okay, that's the open calculation. So it's a more realistic um, the process, especially when you more realistic process calculation, especially when you inject some gas phase and gas is coming out all the time. But unfortunately, this open calculation and the enthalpy calculation cannot be calculated simultaneously. It's not allowed in the fact stage. So if you're using just the constant temperature, yes, you can use open calculation. But as you see here, if you want to set actually the enthalpy as a certain value, delta H as a certain value, the open calculation is not activated, or it doesn't actually allow you to do the calculation. Okay, so just keep the normal and this one, and because we want to see the temperature change simultaneously. And then do the calculation. Then it takes a little bit longer time than the usual isomer calculation because the adiabatic calculation require much more variation of the temperature to find out what's the actual temperature of the final condition. Okay, so now you see that there's the 1500 degrees Celsius, and then there's the liquid metal and the carbon and the other one. So there's almost no change in the chemical reaction here. And if you go to, for example, about 10, and you see that there's some amount of CO is forming, and the carbon is still 3.8%, so it's very small. And then you have the liquid slag is started forming, and liquid solid is already started forming. And for example, if you go to the 0.8, now you have the about 500 grams of liquid metal is forming here, and the carbon is much higher, still very high. And the liquid slag is forming, and then already started forming some solid actually also, the slag as well. So unfortunately, this 10, A equal to 10 is not sufficient even to remove the carbon to the 1%, okay? And the temperature is pretty low, okay? So we have to, in this case, inject more oxygen, okay? So let's say up to 15 every 1, okay? And then let's do the calculation again. And the reason why we actually see the difference between the presentation, actually the result, and the current fact stage calculation is the composition of our ferroalloys, the ferromanganese, the alloys we saved as a stream is different. Okay, so depending on actually this initial actually the ferromanganese, you could have the different result, of course. Okay, so now if you go to the 15, so 1660 as a 1500 degrees Celsius, the last one, A equal to 15. Let's look at that. The result is 1660. Okay, and the carbon is still actually 3%. It's not going down. And then your slag is all gone, and it's become complete solid slag. Okay, there's no liquid slag forming. So under this condition, the flux amount even is not actually very good. That's what it means. Because we have to enter the proper flux amount, proper oxygen amount to have the good decarburization of the ferromanganese alloys. And so this is actually the kind of the thing you have to vary with the A value and the B value simultaneously to find out the most optimum process condition. Okay, so you have to do the dose exercise if you like, and to find actually the good value. And the reason why, for example, the reason why we have so bad result here is very simple. So let's go back to our presentation here. In our presentation, this the ferromanganese we produce as a stream file. This is 100 gram. So per 100 gram, we enter this amount. Okay, this is reasonable amount for 100 gram. But But if you actually now look at it here, this is what 500 gram of the ferromanganese you are talking about. And for this one, at least you have to enter 5 times more value of the B and A to get the reasonable actual result. Okay, so let's try that again. So 5 times. So this should be 1.5, and then 5 times 0 to 10 to 0 to 50 every 1. Okay, then you can get the probably more reasonable result. Let's start again. Okay, so this is kind of the good exercise to show you how to actually optimize your process. Okay, so finding proper operation condition. Okay, so the process is actually taking a little bit longer time. So typically when I do the research or when I do the project for the company to find out this kind of optimal condition, we search all the variable like this and try to find what's actually the most optimal condition. In this case, we are using very simple actually flux, but in reality, you can enter also some alumina and some other thing. And then also the alloys we have here is very simple alloys without containing any other phosphorus or sulfur type of the impurity. But in the real actually the process, you could have those kinds of impurity as well. So not only just removing the carbon, you have to also consider how to remove those kinds of impurity simultaneously. In order to do that, you have to do the proper design of your plugs in the end, which become the slag. Okay, so all these kind of things you have to consider simultaneously, and also you have to consider temperature as well simultaneously. Okay, so there's a lot of calculation. So let's go to so there's the 24 calculation in the first one here, 25 calculation showing in the first sheet here. And so let's take A equal to 24 and let's look at what's the result. Now the carbon is 1.9%, it's quite reasonably low. And then there's slag is forming, and then there's some solid actually slag is also forming, Ca2SiO4. Okay, so let's move on further. And if you want to go to another 25 actually calculation result, go to this one. And then let's go about, let's say, about 33, A equal to 33. Then CO is like this, and the carbon amount is less than 1%. Okay, that's quite promising. This is what we want to target first. And then our slag is the 14 gram of SiO2, about 15 gram of the CaO, and 68 gram of MnO, very high MnO. And then we have about 2.9 gram of the MnO monoxide, MnO and CaO, MgO kind of monoxide is forming here. Okay, so it's a little bit too much because a little bit too less or too much because we have monoxide is forming. Okay. And then if you want to actually see this result, the overall result again, we can actually now go to plot output and then plot the result. And then let's look at the overview of the phase amount with the A. Okay, axis. Now if you want to see the overview, then you have to go gram of each phase, and then X variable is alpha, and refresh, say okay, and then we have to select the gram of what, select all stable phase, okay, say okay, and then plot. Then we'll see that okay, there's slag is forming and there's liquid metal is forming, gas is forming, and this one, if you double click, you can see that this is slag number one, I'm sorry, this one, the bottom one here, if you click, it's MEO. So MEO is still remaining up to about this 37 actual calculation. Yeah. So when you take, for example, if you want to get rid of your MEO, you can go a little bit further. So it means you can go A alpha equal to about 38. Okay. Then you'll see only slag, gas, and liquid metal is forming. And also you have to look at that liquid metal is decreasing quite a lot with the increasing of the amount of the A, and slag amount is increasing drastically after this position here. So it means most probably after this one, the carbon is not actually reducing that much, and eventually you are start to oxidizing a lot of the manganese. So that's why liquid metal is decreasing, and then slag with MnO is increasing a lot. Okay, so I think you have to think about the changing of the flux to have the better condition. But nevertheless, let's look at about this range, about 38. Let's say close it. And then if you go to the result for 38, the temperature is 1831. It's a little bit high. And then you have the CO gas. And then look at this. A lot of the Mn is evaporating because it's too high temperature. And then your carbon is actually less than 1%, way less than 1%. It's about 0.6% now. And then your manganese is 88 and iron is 11. And the metal, the initial metal was about 500 or something, and now it's 440. So you lose a lot of the metallic, a lot of the metal, liquid metal. And you have 21 gram of slag. Slag is 80% of MnO. Wow, it's too much here. You are losing a lot of the manganese to the gas phase as well as to the slag phase. So I think you have to actually look at the proper flux condition and the oxygen injection amount and the temperature as well. This is very high temperature too. Okay, so those kinds of optimized condition can be found by doing many calculation like this. And one of the actually the calculation result was shown before here for the initial ferromanganese of this condition in this case. Okay. So just go and then try to do this type of the calculation by yourself. It will be very interesting example. Okay, and if you have a question, you can always contact me too. Okay, thank you very much.